Hi, Colin. I have the problems that you sent me here. I'll just go through them one at a time here. So we're doing the partial derivatives, and so when we're doing the partial derivatives, we're just going to take turns taking the derivative with respect to x and with respect to y. So let's do x first. And so what we're going to do is treat y as a constant when we do it according to x. And so the derivative here for x squared is just 2x, and then we've got the y as a constant. The ln of x, the derivative is 1 over x, and then for y cubed, we don't have an x value there, and so we're not going to get a derivative for x in that term. So in the second part, if we take the derivative just according to y, then we're going to get just x squared because the derivative of y is just 1. And then ln x is not going to give us a derivative because there's no y term there. And then the y cubed is going to give us 3y squared. And so those are just the partial derivatives for that function. Okay, so when we're doing the double integral, we're going to start on the inside and work our way out. So we're going to start with the integral from 0 to 1 of 8x plus 6y. And then we are going to do that with respect to x. And so our integral becomes x squared, which means that we need a 4 in front in order for that to become 8x when we take the derivative. And then we have the plus 6y. We're going to evaluate that over 0 to 1. And so when we substitute 1 in there, we're going to end up with 4 plus 6y, because we're just substituting in for x. And then we're going to be minusing 0. And so we end up with just 4 plus 6y. And so now we are going to take the integral over 0 to 2 of 4 plus 6y, and this is dy this time with respect to y. And that's going to give us 3y squared plus 4y, or the other way around really, 4y plus 3y squared in terms of the order of those terms. And then when we substitute in the 2, we're going to get 3 times 2 squared, which is 4, plus 4 times 2. And then we're going to have minus 3 times 0 plus 4 times 0, so that's all going to be 0. So we have 12 plus 8, which is 20. And that's the value of the double integral. For the volume of a solid rotating around the x-axis, we're going to use the formula that I've got here, pi times the integral of y squared dx. Y squared is, well, y is f of x, and so y squared would be f of x squared. So here we have root x, so if we square that, we just get x. And so what we're actually going to do for the volume here is we're going to take pi, and then we're going to take the integral over 0 to 9 of x dx, and so that's just pi times x squared over 2. And we're going to integrate, or we're going to evaluate that over 0 to 9. And so we end up with 81 over 2 pi minus 0 over 2 pi, which is just 81 over 2 pi. And so that is the volume of the solid. Okay, so for the last question that you sent me, they're saying, hint, use integration by parts. And that's because we have two functions being multiplied here. And so what we have to do is choose a u and a dv. And so one of those two functions has to be a u and one has to be a dv. And the best way to choose is to try to choose u to be one that's going to simplify to a constant soonest. when you're taking the derivative. So if I choose u to be x, then the derivative of x is just 1 dx, and so it's already simplified to a constant in the first step, which is great because we don't want to do integration by parts over and over and over again. So once I've chosen u and dv, then I'm also going to figure out du, which is the derivative of the function u, so that's just 1 dx. And since I chose the other thing, which was e to the negative x to be dv, I'm going to integrate that and get v, which is negative e to the negative x. And so the integral, the formula for it is uv minus the integral of v du. So all we have to do now is fill things in. So uv just means x times negative e to the negative x, and then we're going to minus the integral from 1 to infinity of v du. So that's negative e to the negative x times du, which is just 1 dx. And so if I simplify this a little bit, I'm going to get negative x times e to the negative x minus the integral from 1 to infinity. Actually change that to a plus because we've got a negative times a negative here. Okay, negative times a negative. And I just have e to the negative x dx to integrate. And so that's easy because it's just one function now. So I have minus x e to the minus x plus the integral from 1 to infinity of e to the minus x dx. And we know that that integral has to be negative e to the negative x, like that. And we're going to evaluate that from 1 to infinity in the next step. Just move this up a little bit here. Okay. And so let's put brackets around this whole thing and evaluate our integral over 1 to infinity. So if I start by putting in infinity, then I have negative x, negative infinity, over e to the infinity, which is still going to become 0, plus, minus, because that's plus and minus there. So minus e to the negative infinity is 1 over e to the infinity, and that's going to go to 0. So that's with the infinity. And then we're going to minus these at 1. So I'm going to get negative e to the negative 1, and then plus, or minus, minus again, negative, e to the minus 1. And so what does this make? This is going to make 0 in the first bracket, minus, and I have negative 1 over e minus 1 over e. And so that's minus 2 over e, which is equal to 2 over e, and that's the value for the integral.